Today, we're going to begin a series on integration. These videos are mainly for students who have already learned the basics of integration at their intermediate level and are now in their first year of university. But don't worry, if you're still in the intermediate level and want to get ahead, this video can still be very helpful for you. Now, I expect that you are already familiar with these basic integration formulas. We won't be starting from absolute basics or baby steps. Instead, we'll build on these formulas and move forward from here. Before we dive in, let me quickly explain the method we'll be using in this series. Instead of using the usual substitution method, where we let a variable be u, I will be using a visual approach. We'll use a rectangle, which I will refer to as a box, to highlight the part of the expression we want to focus on. Then, we will differentiate what's inside the box, and the remaining part will be placed inside an ellipse. So for any question, I will first place the part inside the box, and after differentiating what's inside the box, the rest goes into the ellipse. After that, we will set the ellipse apart and remove it, and then apply the basic integration formulas to what's left. Let's make all of this clear with a few examples, and let's start with the first example. Take a look at example 1 we have got here. We need to integrate this function. Now, if you put the box around the denominator, we don't get what's in the numerator. So this, let's say box is equal to x squared minus 9x plus 1 all to the power of 1 by 2. And the differentiation of the box gives us this. You can see that it isn't the desired result because it does not directly give us just the numerator, 2x minus 9. This means we cannot use the logarithmic integration formula here. So we'll try a different method. Notice that inside the square root, if we differentiate what's inside the under root, we do get the numerator, 2x minus 9. And that's a good sign here. So now we'll rearrange the expression and rewrite it like this. Now we can apply the power rule for integration. But before that, let's go over an important rule. You're not allowed to integrate the operator unless the derivative of the box is present outside the operator. Once this condition is met, we are going to be removing three things: the integral sign, the differentiation of the box, which is the ellipse here, and the d of x. Then you are ready to integrate the remaining part using the power rule. Now let's continue with this example, and let's finish it up. We will take the power expression as the box. Box is equal to x squared minus 9x plus 1. And the differentiation of the box is going to be 2x minus 9. We'll place this inside the ellipse. Now we remove the integral sign, the differentiation part, and the d of x. We can finally apply the power rule over the box here, like this. After integrating, don't forget to add plus c at the end. Now let's move on to example 2. In this example, we also have to integrate a fraction. Just like before, our first step is to look at the denominator and place it inside a box. When we do that, we notice that the differentiation of the box is not found in the numerator. You can see it here. Hence, this method is not working for us. So just like the previous example, we try checking if the differentiation of what's under the square root matches the numerator. So let's do that. As you can see, that it doesn't work again. So we'll have to give it a different approach. We can simplify the expression under the square root using the completing the square method. Let's call this part working 1 or W1, and focus on this expression. Take -1 common. Now complete the square. Now, let's rewrite our expression like this. You can see that this looks familiar, and it matches the standard integration form for the sine inverse. Now, let's compare the sine inverse integration formula with our original expression, and let's identify the parts. You can see that the box is x minus 4, and the derivative of the box is 1. The numerator is also 1. So we are good to remove the three things: the integral sign, the derivative of the box, and the d of x. Also, the constant under the square root is 16. And since we need it in the form of a square, we're going to be taking the under root of 16, which is going to be 4. So now we have also found the value of a, which is 4. So we are finally going to apply the sine inverse integration formula and write up our final expression like this. This is our final answer. Now let's do the example 4. In this question, we are asked to integrate this expression. Remember that whenever we see a square root or something under a root, we try to simplify it in a way that removes the root. For trigonometric integrals, like this, we often use trigonometric identities to do that. Let's take this expression inside the root and work on it separately. Let's label it as W1, the working one. To simplify this, we remember the useful identity involving cosine of double angles. We know that the cos 2 theta is equal to 2 cos squared theta minus 1. So in our case, the theta is equal to 2x. Let's rewrite this. Cos 4x is equal to 2 cos squared 2x minus 1. Now let's rearrange it so 1 plus cos 4x is the subject. That is equal to 2 cos squared 2x. Now substitute this back into our original integral expression under the square root. We get this. We can simplify this by writing under root 2 and under root cos squared 2x. You can see that the square and the under root cancel out, leaving behind this expression. Now, writing it back in our integral, it becomes this. We can take the under root 2 outside the integral. Now let's try to integrate the cos 2x. Now we can place 2x inside the box, and cos is our operator here. We already know that the integral of cos gives us sine, and when we take the differentiation of the box, it is 2. So while integrating, we divide by 2 to balance things out. Hence, we are going to be writing our final expression as 1 divided by 2 sine 2x plus c. This is our final answer.